Right, good morning. This is the last of the revision classes, the last of our lectures for EGM37. We call it Revision Class 2. I'm going to start off where we stopped last week, but before I do, just one thing that I want to show you all, because I'm not sure if you're aware of it. All the builds that you had done during your practicals had the following settings. So it was on titanium 6.4 or Ti6.4, Ti6Al4V is the official name of the alloy. It used a layer thickness of 60 micron. Okay, so I may have told you 50 micron is the normal layer thickness, but it was a 60 micron on this setting. It was a meander scan strategy. It used 400 watt laser power, point distance of 80, and an exposure time of 60. You're welcome to come back up to my office anytime over the next few days, week, or whatever, if you're still working on your assignment. Some of you guys came up to get the costing, and you needed to pick out the right material in Quante M so that you can do some costings of your parts and things like that. So that's the one which would be, there are various material properties files for Ti6.4, one with checkerboard. This one is the meander one, and it has a 60 micron layer. It might have slightly affected, because it's a slightly larger layer thickness, how many layers you needed, so therefore the time of the build and things like that, if you've chosen a different property file. It won't be not by a large margin. Yeah, make sure you write those down or remember them. Okay. So let's get the PowerPoint open, and just as a reminder, because I can see a few of you here that weren't here last week, so this is what we've covered. A couple of the things, the simulation or computer-aided engineering for additive manufacturing, I've said all along wasn't going to be part of the exam. It was just, that's why it was left to last. There's another item on the syllabus which I haven't covered at all, which is on the socioeconomics of 3D printing, and that always falls by the wayside as well. We tend to go more into the technical details of it. Otherwise, I've tried to cover, just to remind you of the revision tools that are available on Blackboard. You've got revision notes, and you've got, so you've got your revision notes, look a bit like this. Each of the chapters made up of the different parts of the chapter with some worked examples at the end, and then a number of multiple choices with the answers already in there. Then you've got the worked examples, and there's roughly 30 worked examples in there. The typical sort of layout. We covered some of these. We covered up to about, I think, number 11. I'm not going to go through all of them, because we haven't got time to go through all of them. I expect you guys to have a look at them. But what I've picked out are probably the most relevant ones. You've obviously got all the lectures recorded or up there, and revision class from last week. I put it up a bit late, I'm afraid, but this one I'll try to get up today, so everything's there. And obviously, I'm going to open up all those tests again online that were there, so if you want to go back and have a go, they'll have a few extra questions just for your revision. So what we're going to do today is probably start off with a quiz, and then we'll go back to where we stopped last week, which, if you want to see more, will be down there. So let's get going on this. I'm afraid that I haven't had time to put it on Kahoot or anything fancy like that. So there's no music, there's no competition, just some questions. Right, which of the following is not a staple application of additive layer manufacturing? Prototypes, casting patterns, C, tool cavities, D, solar panels. A, B, C, D. Yeah. For what volume of parts is injection molding likely to be cheaper than additive manufacturing? A, less than 10, B, less than 100, C, less than 1,000, D, more than 10,000. A, B, C, D, D. Remember there was one chart I showed you in the applications of additive was showing the cutoff point whereby metal parts, so if you were trying to compare an equivalent process that you can make a part in metals, you might be wanting to compare high pressure die casting with an additive. And by the time you make 10 parts or more, the payoff for the high pressure die casting is, so it makes it a cheaper process, so the economies of scale are very low, so very low volume of parts for additive are economically viable, but once you go past 10, it won't compete with anything. It's quite an expensive way of making parts. Obviously, all you've learned is that there are parts that you couldn't make otherwise, in which case there's no comparison. But with injection molding and the production of 3D printed parts by injection molding, that economy of scale, the crossover with injection molding is much higher. So you can have as many as 10,000, less than 10,000 parts, but it will make it, additive manufacturing will be economical after about 10,000 parts. Okay, so I think I just gave you the answer to that. What volume of parts is additive manufacturing likely to be cheaper than high pressure die casting? Less than 10, less than 100, less than 1,000, more than 10,000. A, B, I'm just checking you're listening. C, D, yeah, A. What does TRL stand for? A, technology ready lasers, technology readiness levels, tessellation research language, none of the above. A, B, C, D, yeah, B. It's not quite so much fun without Kahoot, is it? All right. So I think this is one way just to get sort of started. So which of the following statements is false? TRL level metric was pioneered by NASA in the 80s. TRL provides a mechanism for process reliability during development. The 10th level of TRL is the highest level in which actual systems are flight proven. The lowest level is level 1, and the basic principles of technology observed and reported. A, B, C, D, E, C. There are only 9 levels typically on a TRL scale. At what typical TRL level would the direct metal printing of a structural metal component for aerospace be in? This is all very subjective. A, TRL 1 to 2, B, TRL 2 to 3, C, TRL 4 to 6, D, TRL 8 to 9. A, B, C, D, C. Okay, and that's all depending on who you talk to. You talk to the machine manufacturers, they'll tell you it's 9. You talk to somebody who's actually interested in making aerospace components, and they'll tell you that anything to do with metal printing is quite low TRLs. They're not quite ready to make parts and go in. Metal components are not being flown that often in mass production, anything. All right, so apart from bodies. With respect to metal parts made directly by additive manufacturing, are the TRL levels of plastic parts considered to be A, higher, B, lower, or C, at the same level? A, B, C. A, higher. The plastics technologies are more advanced, they're easier to use, the more adept they are. There are more things in production. Right, we'll skip that. You can see that this is part that maybe not important to think about right now. Remember the Gartner height curve is where technologies went and just came up, disappeared, went through different areas of interest. So from the perspective of the development of additive manufacturing as a process to directly produce parts, which its greatest area of focus is the current, means the current greatest area of focus is A, to increase the size of builds and speed of the process, B, to decrease or minimize support structure use, C, improve the material properties of the as-fabricated parts by considering the entire process chain from upstream powder metals to downstream heat treatments, D, increase computational modeling and CAD software capabilities to take full advantage of the great freedom of design, E, all of the above. A, B, C, D, E. Yeah, E. Basically all of the above. All the different manufacturers are going off in slightly different directions, and you could say that the increase of the speed of the process is very much at the forefront of the new machine. So I was just talking to the technical director of Renishaw this morning, and he wants one of our HDs to go up to second them for a bit, working on the new quad laser system. That quad laser system is all about increasing the rate, the build rate, because if you have 4 lasers working in different sections of the layer, you're able to build up the part at potentially 4 times the speed. Yeah? But having 4 lasers firing at the same time means that you've got more condensate, more evaporate, the lenses get covered quicker, so there's more problems within the process. So, just an example. But all of these are areas where there's a lot of work being done. Okay, I think this is one of the last ones. In terms of the pros associated with the additive manufacturing, which of the following statements is false? AM does not give unlimited design freedom, but there is a great design freedom. AM is not rapid, but is agile and adaptable. AM does not have 100% material usage, but it's getting closer. AM is suitable for all applications. Which of those statements is false? A, B, C, D. Correct. It's not suitable for all applications. It doesn't necessarily make a pizza cutter that well. It doesn't even make bottle openers that well sometimes. But I don't know if that's the process or the bottle opener itself. But it can make things that other things can't do, but it isn't necessarily a replacement for all processes. It's not necessarily going to be cheaper, even than, or less wasteful than other processes. It depends on the component. But enough of that. Okay, so where we left off in terms of some of the examples last week, if I remember correctly. We covered the basics, layout. I think we stopped at example 10, where we worked out some costs of building some cylinders, how we would lay out the cylinders on a plate, what the best layout would be. Very simple component. It wasn't really about that. It was just about how you would approach putting something in. Potentially that part could have been much more complex, but then you could have a cylindrical envelope around it, so you would use that as a sort of first estimate as where you'd locate it. Obviously, Quant-AM does all of this for you now, but it's worth knowing sometimes Quant-AM doesn't get it quite right. So you need to go over the top of that. Just what I've done on this, and I hope we can cover it by the end of the class, is that I'm just giving you a few reminders of parts of the chapter, then I'll pull up one of the examples which I think is relevant, and then we just move on. In terms of the physics of AM, we did cover a little bit about the different types of industrial lasers that are used, and specifically we focus then on some of the lasers that are used for powder bed and blown powder. CO2 lasers on the one end, where you've got sort of a larger wavelength of laser. They're used more typically in the powder deposition, and then on the powder bed, when we're using more the 1 micron wavelength lasers, and ytterbium fiber optic lasers are typical of all of the powder bed processes now. But they have been through iterations where they've used different types of lasers. It's just that the ytterbium fiber optic laser is the most efficient in terms of the energy use. There is quite a lot of wasted energy, so if you do compare, and that's something else we've had a look at, if you compare directly melting a metal through something like induction melting, you might end up with maybe 1 kilowatt hour per kilo of metal melted. When you're using a laser to melt the same amount of material, you're using 20 times that or more. And part of the problem is the laser has to be stabilized and thermally cooled all the time, so you have a 1 kilo for our 200 watt or 400 watt lasers, we'll have a 1 kilowatt chiller continuously cooling the laser while the laser's doing the work. So not only does the laser use the energy to melt, but it also needs to be cooled at the same time. In terms of and from there we moved on to a little bit more on the physics, and a lot of this is described by, at its most basic, through the heat equation. The heat equation takes this form, where you've got the convection diffusion on the left-hand side, and you've got the conduction on the right-hand side, and then you've got a heat source through radiation. We talked about the different modes of heat transfer. There's a lot of complex physics going on, down on quite a small scale, often very difficult to see. So we talked about the interaction of the laser. So you've got radiative radiation coming down, interacting with powder. There's phase change, you're melting the powder. It's going from solid to liquid, and then solidifying back into a solid. You'll have some evaporation from the metal, and that produces a condensate plume, which flows off the top and will then very unhelpfully cover the lens and inside. The evaporated metal will condensate into very small particles, nanoparticles. There's obviously conduction and very high cooling rates going on. So when you have actually melted the powder and that starts to solidify, you've got a thick base plate underneath which draws away the heat very quickly, so you've got high cooling rates. Those high cooling rates tend, if you look at it in terms of the type of microstructures that you get in the materials, those high cooling rates give you very different microstructures that you might have from casting or from other slower cooling process, like hot isostatic pressing or hot pressing. And then, of course, you've got convection going on in the same thing, and convection can take come in various forms. You have convection because you have relatively cold inert gases like argon flowing through the chamber. The argon is there to stop the rapid oxidation during the melt. It's there to make sure that it doesn't explode, that you're heating up a powder that could be pyrophobic. Other forms the convection takes is then capillary and Marangoni convection, but you also do have sometimes with larger laser, you will have thermal convection actually within the melt pool. The Marangoni convection is the one that's particularly important for the smaller scale lasers, and that determines how wide and how deep the melt pool is going to form, and the surface tension and Marangonian surface tension combined together will also determine whether or not the melt pool will stay together in a single track. How deep the melt pool goes, so let's talk about the melt pool a little bit. Very similar to welding, but on a very small scale. The melt pool is made up of the main components. You can define it by length, width, and depth. The Marangoni convection that happens within that melt pool will determine the width to the depth ratio, which is very important. These are the sort of things that we talked about in terms a little bit of controlling the process. You don't have to worry too much about this, but there's a couple of phenomena that happen when at the level of the melt pool. One is the instability of the melt pool. So the melt pool can break up, and that's determined by this plateau Rayleigh instability. It depends on the perimeter and the length of the melt pool, which is driven by the cooling rates and the convection and all of these things together. But different alloys will have different stability. What happens if you get an unstable track is that you'll get balling, and the balling then is an area that you want to avoid on your process map. I think we actually covered this last time, which was just to work out some efficiencies. So I'm not going to go through that one again. What I'm going to go through quickly is, now this is leading to the process control aspects of the machine. So you should know by now, there was a test on Blackboard, we've been through it in the lectures a few times. You can have lasers which work in continuous mode, or you can work with lasers that are modulated. The machines that have made your parts are modulated. So it's defined by a series of spot welds happening in very close succession in both time and distance. So on the diagram on the right there, what are the distances D1, D2, D3, and D4? Well, D1 is the adjacent distances between subsequent points of the laser touching down. That's called the point distance. D2 is the hatch offset. So if you think of this as a single hatching of the area, we have a sort of the contour boundary, which is this line on the inside, and then everything is made to come up as close as possible to that contour boundary. That distance D2 there, we call it the hatch offset, means that you can try to get as close as possible. It allows you for a bit of overlap. Now, all of these things are machine dependent and material dependent. So you can set it on the machine, but it's not necessarily what you're going to get when you actually melt it. Okay, that's the differentiation we've made all along. So, and the layer thickness is the same thing. There are settings that you put on the machine, but then the material will respond differently. So when you melt a spot of titanium with all the same settings as you might melt a steel spot, they're going to have different widths, different depths, and they're going to solidify in a different way. So we use these settings obviously then to as our material property files, which we will optimize to work as well as possible for that material. But they are just machine settings. So D2 is the hatch offset. D3 is the hatch spacing. So the hatch spacing is the one, so point distance is along the line, hatch spacing is across the surface. And here we've got an additional hatch border offset, D4, that runs all the way around. Within the border, you might have the laser running around. It forms like a skin around it. So you might do the lines, and then you finish off the border with a single laser setting that goes around. It might be sort of quite low power, high exposure time, and it makes quite a kind of streaky sort of line around it, which has a lower surface roughness, and that's why it's used for a skin setting. The lines A and B are the hatch boundary and the contour boundary. The contour boundary is the inside part. It's the contour of the part that's being made. Okay. So you're going to see this a couple of times. We've been through it. It was actually one of the tests, online tests, was if you have a single 10mm sided cube and you're given the data on the right-hand side there for the point distance, exposure time, etc., then you're asked to work out what is the energy density going into that cube. And you can use a series of steps to get through this. So how many times is the laser exposed upon a single line? How many times is the laser exposed across a single layer? And then, so what is the maximum input energy for the single layer? How many layers are required to build the complete cube? And that depends on the layer thickness. And what is the theoretical maximum energy the entire cube will require in joules per cubic millimeter? All right, so that's a pretty set question that has come up a few times. By now, with that knowledge that you have of what a point distance is, what a hatch spacing is, and what the layer thickness is, those three values will give you that answer. So you should be able to work it out. You don't need equations. Okay? How many times is the laser exposed along a single line? Well, it's the side of one side, or the length of the cube, divided by the point distance. Yeah, and that gives you that there are 133 times the laser touches down on its way down. The hatch spacing on this is 100 micron, or 0.1 mil. So what we want to do then is how many times is the cross-sectional area. I don't think I've got a pen. The cross-sectional area, which is 10 millimeters by 10 millimeters, and you've done one line, so there's going to be, with a hatch spacing of 100 micron, means that there's going to be 10 lines in that, in the cross direction. So the total number of points that the laser comes down on a 10 square millimeters is that 13,300. 13,300 in a 10 square millimeter square. So the duration of the exposure for the slice is the number of points times the exposure time for each point. And the exposure time is 50 microseconds. Yeah, so we multiply 13,300 times the 50 microseconds, and we get 0.665 seconds. So the energy, which is power times time, gives us the slice energy in joules, which is 150 watts, which is the setting for the laser. 150 watts there, times the duration of the exposure of the laser across the whole of that 10 millimeter square section, and that gives us 99.75 joules. Okay? How many layers are required to build the entire cube? So now we go up into the third direction, which is vertically upwards, and we take the cube height, which is also 10 millimeters, divided by the typical layer thickness here, which is 50 microns, or 0.05. So again, we have 200 layers on the way up. So it means that each of those layers is built up of a square, which uses that many joules. So the entire energy, is the number of layers, N3, times the energy at each slice, which is 200 times 99.75, which is 19,950 joules. So we can divide that by the volume of the part. The volume of the part is 10 mil by 10 mil by 10 mil. Or 1,000 cubic millimeters. So therefore the laser energy input per unit volume, or the joules per cubic millimeter, is 19.95. Okay? Can you do that? So if I were to change those numbers slightly, you could work your way through those steps, yeah? Okay. Can you remember off the top of your head whether that 19.95 joules per cubic millimeter was on the low side or on the high side of a typical run? I'm not going to show you here, I just wonder if it was in your head. Remember I showed you a densification curve with a scale at the bottom, which was this laser energy density. Yeah? What was 19? Was it on the low side or the high side? Unfortunately, I don't think I've thrown that slide in. So it's on the low side, okay? 19.95 is very much on the low side. Typically, we'll be working in something like 50 to 60. High side, depending on some materials, prefer to have a high energy density. You might be working up at 100, 120. But 19.95 would probably lead to 40%, potentially lead to as much as 40% porosity, the massive porosity. So it's not a brilliant setting. That takes us on a little bit. So we talked. Now That's the standard calculation for the energy density. We've talked about how that can be linked to the porosity. Other AM defects that we've talked about a lot, residual stress, because of the difference in between, so you've got very high temperature at the point of the melting, depending on the alloy. You might be as high as a couple of thousand degrees for a very short duration of time, but although that cools, it means the entire surface has a high temperature. Each layer has a higher temperature, and you attach to a very cold base plate, and you have support structures possibly running down the sides, which means that you are literally clamping a hot object to a cold object, and as the entire thing forms, those stresses that are keeping it clamped are retained within the part. So you've got residual stress. You guys have seen yourself on your own parts that geometrical shrinkage can also be significant. Delamination of layers, possibly linked to residual stress. Now we're talking about melting metals, so you do get potential pitting and toppling, sinking as it solidifies. Surface roughness, you saw your parts when they came out, you felt them, they were rough. Typical surface roughness are in the order of 12 to 15 micron, RAs of 12 to 15 micron, which compared to most processes, even casting, is quite on the high side. And that needs to be finished off. And step geometries is the fact that we are dealing with a digital technology. In this case, the main part of the digitalization is the fact that we have discrete layers. So we're trying to match possibly vertical curves with discrete layers. So that's some of the typical defects, and you see then, because of not just the defects but the process itself, you'll see these defects in the properties. Variable surface roughness, non-isotropic properties, possibly non-isotropic, both because of the high cooling rates in a directional form, but also the porosity. There's a large scatter of the properties in mechanical properties particularly, and you might have much lower mechanical strength in the vertical direction than you do in the horizontal direction. These also lead to reduced fatigue life and creep life, and reduced high temperature strength, corrosion, etc. So I'm not going to go into these, what porosity is or residual stress. I'll leave you to go back to the notes to remember what all those are. We've talked about them. Some very basic stuff. I think this has fallen in from a previous chapter. What is the basic definition of additive manufacturing? The process of joining materials to make objects from 3D model data, layer upon layer, as opposed to subtractive. So the two things to remember about the ASTM definition of additive is that it's based on model data, it's layer by layer, and it's the opposite of a subtractive method. Generic steps, we're not going to go through these, we went through them last week. You got them all right on the quiz, anyway. Two different types of additive manufacturers, one which does not require support structures, one which does. So obviously you know this selective laser melting or laser powder bed fusion, which is the more generic term, requires support structures. You've seen it, you've had to take them off yourself so you know what the support structures are. Blown powder or wire additive manufacturing are two processes which don't require support structures. They're limited by the number of directions in which a robot can position the laser, but they can build onto the surfaces of curved geometries. So you could potentially take the surface of a turbine blade or a aircraft landing gear section, and you could build additional parts onto that. But they don't use support structures. That's quite basic. Building up process maps and the identification of parts with process maps. Typically we'll start, most experimentation gets done whether on the large scale where we're talking about welding or powder bed. right the way down the powder bed, you'll start just making tracks with the material and looking at the influences of mainly power and speed. Okay, that's the sort of main type of process maps, and you'll have different parts of the process map. Here you can see F to A. So on those process maps, these regions that you have on the process map are the ones where you've not successfully managed to fuse the material, which will be in track F, through to poorly formed tracks, which are fragile D tracks. Irregularly, you get the occurrence of balling. Yeah? So you're potentially moving too fast with not enough power, or there's that Marangoni problem was causing the melt pool to break up and droplets to roll off and ball up. And that makes them irregular, and we don't want to have irregular tracks. So certainly F, E, and D are regions you want to avoid in your process map. The whole reason of having a process map is that you can rather quickly determine where you want to be in terms of speed and power. You've then got these regions C and B, which are a bit better, and probably your optimal location is somewhere between the two of them. But then you have the opposite effect, where you're actually moving too slowly, and your laser's got too much power, and then you get the other effect, which is keyholing. Yeah? So, and why do we want to avoid keyholing in powder bed? Is keyholing always a bad thing? No, it's not. Sometimes you want to have keyholing. If you are trying to spot weld, say you had two plates of metal together, and you wanted to spot weld through it, you might want to actually penetrate the weld all the way through the two metals to act like a sort of staple on the way through. Keyholing isn't always a bad thing that needs to be avoided. In our case, though, it's not necessarily a good thing, because you are going through into the layer below, and you're introducing porosity on quite small distances. So if you introduce porosity through it and go into the next one, then you're actually getting more porosity in the part. So in powder bed, it's something to be avoided. But these are the two areas where you want to, if you see a process map, ensure that you know that balling happens in the high speed, potentially low to medium power, and then on the opposite effect where you got, balling happens high speed, medium to high power, and the keyholing at the low speed, high power. So I'm not going to go too much in detail about the keyholing. We've already done this, how it forms and what a keyhole weld looks like, which looks more like this, like a shark's tooth. And then you can see the evidence of balling and the droplets there on some tracks which have been laid in stainless steel. I'm not going to go through this example either, because we've just done it. All right. So again, this working out what the laser input energy volume. These are slightly different numbers here for the same problem, and you can see that the final outcome here for those settings was a laser energy density or laser energy input volume per volume of 118.8. So you remember I was just telling you now that 118.8 would be on the higher end of the power density, energy density, sorry. So what's the relationship with density and porosity? Well, they're inversely proportional, so the higher the density, the lower the porosity, and so on. We can look at porosity, we can try to measure it using Archimedes, which is fine for porosities of higher than 2-3%. But once you get porosities lower than 1%, it's actually quite difficult to try to differentiate using Archimedes. So you might use an optical microscopy or something to section the part and count the pores that you can see somehow, or use image analysis. And that will enable you to see lower quantities of porosity below 1% to 0.5%, which is where the machines are at the moment. So we might use design of experiments to set out different energy densities or different power laser power input settings, and we will measure the density of each of those, and that density value that we measure, or the porosity value that we imply from the density measurement, will indicate, will allow us to select the best set of machine parameters for that material. Okay, so we've been through all of that. In terms of material properties, I'm not going to talk a lot about this, but just the sort of take-home message from, I think it was the week before last, we did the lecture on material properties. You can post-process as-built material, and you often expect to do that with additively made parts. At minimum, you're going to do a heat treatment, but then possibly you might do something a bit more invasive, like a hot isostatically pressing the part to get rid of porosity. It doesn't only affect and close off porosity, it also realigns the differences between horizontally built material and vertically built material. Typically, you will have vertically built material test bars will not be as strong as horizontally built test bars, and that's typical across most materials. It is dependent a little bit on the machine settings, so not every paper you go to will tell you that, but on the whole, that is the case. And you can see here the results for three heat treatments. One of them is a hot isostatic pressing, which also involves pressure, but you can see how the heat treatment, and another thing which is typical of the tensile properties of a material which is made by additive, because of the high cooling rates, you tend to get quite brittle materials. Not just the high cooling rates, but potentially the porosity itself adds to the embrittlement of the material. There's also potentially higher oxygen that you get than you do with other materials. So, but altogether, all of that has the implication that they are less ductile as built than you would expect. So titanium 6.4 has a typical elongation value of around about 17–18%. The as-built material coming out of the machine, what we found is can be as low as 1%. Very, very brittle. It depends a little bit about the quality of the powder. It depends on the levels of oxygen in there. But certainly the heat treatment, the level of heat treatment that's required on this shows that it's not just necessarily the composition having been affected, but it is those cooling rates have affected it somehow. So what you get is, as you heat treat it, you return the elongation back to the material, but potentially you lose a bit of yield strength and upper tensile strength. So you can see that happening here with a mild annealing treatment. You've got a range of elongations from 2 to 11%, so quite a wide range of elongation. We go up to a slightly more aggressive heat treatment at 850 for an hour, and you can see that then the range shifts up. So we've got it from about 5 to 13%, but we've still got quite a big scatter between the results that are coming through from the vertical built tense bars and the horizontal built tensile bars. And it's only when we actually hot isostatic press it that we actually get something similar to what we should have in terms of the elongation of TI64 and a much narrower scatter of the properties according to their direction. So that's just a bit of summary of the mechanical properties. We talked about various powder. We talked about various manufacturing methods for powders, and we talked about how we characterize powders. We talked about different measurements that we take to characterize the powders and how that helps us set up the quality of the feedstock, the powder feedstock that comes into the machines. One of the things we focus on, and I've got an example here, is just how you can use the accumulative distribution. So all the powders have a range of sizes. We have size fractions with D10, the D50 and D90, which is based upon the volume of particles which have less than a certain size. So 10% are in a certain size fraction or below a certain size, 50% below that certain size, and 90% below another. In order to derive from a cumulative size distribution what these size fractions are, all you have to do is when you have a cumulative curve like that, you go to the 10% for the D10, and you can see that if you come across, you can pull out 24 micron there, as all particles, 10% of the particles are below that 24 micron. The 50 means that if we come across at the 50%, that 36, and that gives you 36 micron, which means that 50% of the population of particles in that sample is below that 36 micron. And the same for the D90. We have that 90% of the particles are below the 53 micron, which means that 10% are over it. Okay? We did say, and there's one of the things to remember, is that the powder size distributions typically will have in powder bed, laser powder bed, we will have D10 about 20 microns, D50 about 30, and D90 at about 50. So our size ranges, nominal size ranges, are 15 to 45 micron with those kind of size distributions. That's for laser powder bed. When you go to electron beam, you use larger particle sizes. And they will be as large as 120 microns, but maybe with averages around about 90 to 100. Okay? That's just an example of what has come up before in the exam. We talked about the different manufacturing routes. And also what powders look like. That's titanium powder there on the right, but it's not obviously, well, it's not obviously, but it's not a gas atomization route, which would give you very spherical powders. So this is probably not going to flow very well. It is quite coarse. You can see that the powder, the particle sizes here are well above 100 microns. You can see the scale bar there, possibly even 200 micron plus. And you could potentially say this might come from mechanical milling, where it's been ground together, or some form of chemical decomposition. There's no dendrites in it, which is another indicator of it being electrolysis or some other solidification form. And I think here that would, those are typical of the sort of hybrid, dehybrid process, but you couldn't rule out some sort of mechanical milling. Those are the 4 highest categories of different types of powder manufacturing routes. We've focused a lot, obviously, for the additive-based powders, which generally come from gas atomization, which is a physical process. Okay. When Keith gave the talk to you guys about, he also mentioned a little bit about plasma processes. I'm not expecting you to remember this. It's a bit of a, but yeah, you can use a plasma instead of using high-speed induction melting and high-speed gases, which is traditionally the gas atomization route. Okay, we're not going to have time much more. I just want to focus one last one on the chapter 10, which is on the design for AM. So you'll find that all of these are in the book, so you can follow these at your own rate. I'm just going to maybe pick out some. So one of the examples is a real example, which was trying to get this T-shaped wall built. A very awkward build for us because it was quite a thick section, 8 mil base. We tried the first one, that failed. We located at 45 degrees, thinking everything is at that 45-degree angle, if you put it like that. But that wasn't necessarily. We found that the only real way to make it was upwards. So just to show you some of the failure, when you locate it flat on the plate, this is an in-process tear that has happened, or delamination or tearing that happened during the process. And it is, you can see this classical sort of banana shape where the part has tried to expand outwards like that, and it's taken away from the support structures, and it's ended up ripping itself apart during the process. But you can see that it wasn't catastrophic in the sense it didn't stop the process from building, and it carried on building after that, and it went all the way to the top and then realigned itself. So each of those, on the actual middle part of the wall here, the build was back up to flat again. Locating at 45 degrees was more catastrophic. It did rip up the wiper, and you can see the vague logic which was there to try to reduce as much as possible the amount of support structures, but that was quite unsuccessful. The shape came out absolutely distorted, and there was very little that we could do with that. So sometimes the simplest is the easiest. Just locate it vertically upwards. The least cross-sectional area you've got in contact with the plate on the way up through the build is going to give you the least heat, so therefore you can have the least thermal distortion. That's just something to remember. Minimizing the support structure isn't always as successful, as you can see with those examples. So this is a theoretical example, which is kind of what you guys have been through with your own parts. A very simple shape. The best way to summarize this is through a manufacturing design trade-off table, where you might consider three different build orientations. So the first thing to look at is, when you see a drawing like that, is to look at the size of the features that are there, see if there's any threads, see if there's any awkward shapes, which would mean that it might not go onto the plate, that if you put it in one position, that doesn't make the other part of the component difficult to build, because that can happen. You can have parts which are just so awkward that you can position when you want. You can make that perfectly, and then this damn thing's coming across an angle like that, and you're going to have to. You know that. You've been through that with your parts, so you know that that it can be awkward. In this one, it's not particularly complex, but what we need to consider more in this instance is that you've got potentially a relatively thick wall. You've got cavities. What an accepted size of those holes for this to build accurately is that they be no bigger than 10 mil. Okay, if you give that to me in an exam question and say 10 mil is the smallest hole that I can build, I'll be happy with that. Although you have seen that potentially by modifying the hole that you can build bigger holes, and it's not always that you can always build small holes. So you'd have to probably do some testing of the material. But as a rule of thumb, 10 mil diameters will self-support. So you might be asked to consider three different build orientations and weigh up the benefits or not of putting in that particular build direction. So you've got case 1 vertical, case 2 horizontal, case 3 on its side. So the first thing to point out, okay, I've said 12 mil, 10 to 12 mil. As long as you give me some idea that there's somewhere in that region, that's fine. I'm almost done. So yeah, it's a knock-on effect. Yeah, so come up with a table, design which of the cases, consider the removal from the ease of removal, distortion, concentricity, whether the faces are going to be better in a vertical, so you know that they build, if you have the surface roughness on a vertical build face is better than on a horizontal or one at an angle, because you're going to have the staircasing effect. So you have to kind of consider the pros and cons of each of those and balance them off against each other. Okay, so I've got to stop there. I'm just going to say it's been lovely working with you this term, so I hope you've enjoyed, and I'm sure I'll be talking to you again anyway over the next few days anyway. So, right.